All right, now we did a part of section 3.1 already. The part that we've already done had to do with just the idea that the derivative is can be found by using the limit process, where you get the limit of the difference quotient. And when we did it, you can use this right here, but it's equivalent to just h approaching 0 and having f of x plus h minus f of x all over h. So the first time we did section 3.1, we developed that idea that the derivative is really a formula that enables you to find the slope of a tangent line to the curve at a particular point. So the slope of a line like this, the tangent line to the curve, okay? So rather than needing 2 points and using the regular slope formula, or the difference quotient is actually the slope formula written with function notation, rather than doing that, okay, we want to know what the slope is at this specific point. And so what we can do is let the point move closer and closer and closer and closer to the one that we want, the one that we're using, the one that the tangent line is touching, okay? And so we developed this in the previous video. And then we came and we did problems like these. These problems were both there and also in other sections in chapter 2. Like you also did this in section 2.3. So we did these before. So we did these earlier. Okay. Now we're revisiting section 3.1, but this time when you're asked to do the homework for that, it's going to be okay to use the rules that we're learning in section 3.2 rather than having to do it using that complicated formula and having to do all that algebra. Okay? All right, so let's go back and get some of the basic terminology straight. Okay. So the derivative of a function at x I want you to be thinking that that's giving you the slope of a tangent line to the graph at x. And that means that you're actually getting what the instantaneous rate of change of the function is right at x, rather than doing the average rate of change from one point to another one. Okay? So you know how to do the slope of a secant line using the regular slope formula, and you would know how to get the average rate of change using the regular slope formula. That's what this really is. Okay? So that's the slope of a secant line, or the average rate of change. But when you put the limit as h goes to 0 on it, that's enabling you to get the slope of a tangent line to the curve at a particular point. And it allows you to get not the average rate of change, but the instantaneous rate of change. Okay? Now, various notations for derivatives. So if we had y equals f of x, okay, like if our function was y equals f of x, okay, you might see us use f prime of x. It's a little line at a diagonal. It's not an apostrophe. It's straighter than that, and it's a little line coming towards the f at a diagonal. You might see us say dy dx, the derivative of y with respect to x. If they didn't use the function notation, so like, sometimes they'll give you the function and they'll use function notation, but sometimes they just say y equals 3x plus 2. So if you wanted the derivatives, then you might use f prime of x if they gave you an f of x, or y prime if they gave you just a y. Okay, and then the d dx of f of x is another notation that's used. It's emphasizing that you're doing the derivative with respect to x. This notation is what was used on the sheet that had the summary of the differentiation rules. They use that d dx of something. And then you don't see this one very often, so that one's not very common. Okay, but the other three you do. All right, and then just some terminology. The process of finding the derivative of function, that's called differentiation. Okay, and then we say that a function is differentiable at some spot if the derivative exists there, and a function is differentiable on some open interval if it is differentiable at each x in the interval. Okay. All right, now, if you have a function that's differentiable at some particular point, then it follows that f would have to have been continuous there. That's really the same thing as if f is not continuous at some point, then it's not differentiable there. Okay? But something that's important to understand is that the converse of this, if you switch these two and you said if f is continuous, then it's differentiable, that would not necessarily be true. That's the converse of that statement, and the converse, it does not say the same thing as the original statement. So being differentiable implies continuity, but being continuous doesn't mean it's differentiable. Okay? All right, so a function that is continuous is not necessarily differentiable, is what we're saying. So it's not going to be differentiable at places where there's a sharp point, like that function there, okay? Or if you wind up having a vertical tangent line, like this one. And you can see why those would be problems. Because if the derivative is really slope, then do you see why this would be a problem here? Because the slope of a vertical line, the slope is undefined. Okay? So the derivative isn't going to exist there. Okay? Right? And then when you look at the one in the middle, think about trying to have a tangent line sitting right there. See, that sharp point means it's hard to pinpoint a tangent line to that, to touch it just one spot. Okay? As you're coming this way, okay, you're seeing how the limit of the function coming this way, the limit, if the limit process were used to determine the derivative, we would have the slope being -1. But on this section, if we use the limit process to determine the derivative, the slope would be 1. Okay? So the derivatives aren't the same from the left or the right. But I really just kind of think about how that sharp point right there means you can't settle the tangent line at any spot. Unlike if it had been like a round or curve, then the tangent line would rest right there. And that one would exist and would have a horizontal tangent line. Okay, and then the first case here, right? Though let's say x equals 0. If we're looking at x equals 0, that one, the derivative is not going to exist simply because it's not continuous there. Like I have to lift my pencil there. It's not continuous at that spot. So really, your function's not going to be differentiable if it's at some point, if it's not continuous there, if it's discontinuous there, or if you have a sharp point at that spot, or if there's a vertical tangent line at that spot. Okay. All right, now we did these, like I said earlier, and those are the ones where you looked at the limit as h goes to 0 of f of x plus h minus f of x over h. And you did it the long way. Right now, when you go back in to do 3.1b and you do problems like these are going to be similar to what, or I included some problems like this on the section 3.2. And so when you get to these questions, when you revisit 3.1, you may use, the reason I separated it is I wanted to teach you the shortcuts. Now you can go back. You may use the rules instead of doing this business. Okay? So that's why I separated it. So it is okay. Just go ahead and use the rules on this. So on question number 1, it said find f prime of x for this. Okay. Then get the slope of the tangent line to the graph of the function at those 3 points. So if f of x equals x squared plus 2, in section 3.2, by the way, you might want to, after you do that first part that gets at the notation and some of the vocabulary, why don't you stop this video and go watch the 3.2 video. Okay, then come back to this one and use the shortcut rules. Okay, so watch 3.2, then finish this one. Okay, so in 3.2 we learned to do the derivative of this. We could just use the simple power rule. Okay, and then if we need the slope of the tangent line at particular points, all we got to do is look for f prime at -1, f prime at 0, and f prime at 2. So I'm going to plug in a -1, I'm going to plug in a 0, and I'm going to plug in a 2. So depending on where we are on that original function, the slope of the tangent line might be -2, it might be 0, or it might be 4. Okay? So I want you to picture that, because x squared plus 2 is so easy to graph. It's just a parabola that's sitting up 2 units. So if we're right there at an x of 0, the slope is 0. The slope of the tangent line is 0. But if we're over to the right 2 units, the slope there of that line would be a +4. And if we're over here, the slope of that tangent line would be a -2. Okay. All right, and then we had to review a little bit about equations of lines. So there's more of this if you need it in the textbook. You can look up how to write equations of lines. One way to do it is to use the point slope formula, which is this. And so if they tell you the slope is -3, or you found that the slope was -3 and you know your point, then you can just plug in the y coordinate where y1 is, plug in the slope, and plug in your x coordinate, and then do some algebra to simplify that. Finally, subtract 7 from both sides, and you wind up getting y equals -3x plus 5. All right, now that's using the point slope formula. You could use y equals mx plus b. Some of you do that. If you're going to use that technique, then the y coordinate goes in for y, the slope goes in for m, 4 goes in for the x coordinate, and you actually work on finding the b value. So you add 12 to both sides and get that the b value is 5. But then you have to finish it. So then you go back up and you think y equals mx plus b, and you replace the m with the slope, and you replace the b with 5, and you get y equals -3x plus 5. Okay, So you can use either of those, but you need to be able to write the equation of a line. That's a very basic algebra skill. So if you're rusty on that, you need to be working on that a little bit. I think there's some problems in the text. Gosh, I want to say it's on page 16, but you can look for that if you need it. Okay. All right. So we'll go ahead and do a few questions. I'm going to go ahead and just get these done pretty quickly. So here, if I needed the equation of the tangent line, then I have an extra step to do over what I did in question number 1. First, I would get the derivative by using the shortcut rules. Okay. Then I would be getting the slope at the particular point they gave me. Okay. Then I would be taking that slope and that point and writing the equation of the line. Using the point slope formula, it would look like that. So then you would just clean it up by distributing the 4 and then add 2 to both sides and get y equals 4x minus 2. Now sometimes finding the derivative is a little harder. Like you have a little rewriting to do on this one. Let me blow that up a little bit. So that would really be 3x to the 1/2 power. And so when I do the derivative, the constant gets multiplied by the exponent, and then I have to subtract 1. And then when I clean that up, I have a 3/2 x to the negative 1/2, which is really 3 over 2 square root of x. Okay. All right, so now I'm going to do f prime at 4. So I'm going to plug in a 4 to get my slope. And I get 2 times 2. I get that the slope is 3/4. And then finally, I'm going to take this particular slope and the point and come in and write the equation of the line, just like we did before. So I'm using the point slope formula, plugging in my slope, plugging in the x1 and the y1. So y minus 6 would equal 4x minus 16. And when I add 6 to both sides, I get 4x minus 10. And they did want the equation, so that's why I had to go that far to get it. Okay. A little rewriting is necessary on this last one. I haven't done the derivative, I just rewrote. Now I'm doing the derivative. Derivative of x is 1. And then here I would have a -1 times a -1 would be positive x to the -2, which equals 1 plus 1 over x squared. Okay. So I need now to find out what the value of the derivative is at 1. So I'm going to plug in a 1, and I get 1 plus 1 over 1, which is 1 plus 1, or 2. So now I know the slope is 2, and the point was 1, 0. So I'm back to trying to write the equation of the line. So y would equal 2x minus 2, and I'd be done.